go ahead and start it. Yeah. So this meeting is over like GRPO or an RLHF, and basically, uh, RLHF was kind of the first way to get models to talk to you in a way. So like you have your normal LLM and you train it to predict the next word, but that's only so good. So, well, go ahead and go over here. So that's only so good. So if I ask it like, what is 1 + 1? It could say it was 2, but it could also like continue that, and it could say, well, 1 + 1 is 2, said this person, and it's like, well, those are both as good under the training data, but you want it to talk to you. So RLHF is like, how do you get this thing actually chatting with you? And it's this thing that I think OpenAI made it, and the original one was in it was with ChatGPT, and I think they released a paper. I don't remember if they did or not, but it's this big thing, and everyone's doing it now. And then DeepSeek comes along, and they're like, well, what if we don't do this stupid idea with RLHF where we use something called PPO? I'll talk about that later. And instead, we use something that is actually smart. So we're going to do something called GRPO, and I'll explain that in a second. But essentially, the main idea is you have this LLM. This LLM knows a lot. It doesn't know how to really communicate with you, but you want it to get it in this get it in the mood to talk to you, get it in the mood to do this to respond to you. So changing the probability distribution so that it responds to you instead of it completing. And those are your instruct models.
Sorry, what is supervised model?
Supervised model? That's your so you'll see like SFT or supervised model, and that's your original model you trained off the entire data set, like the entire internet.
Yeah.
And then you align it with RLHF. So aligning, or
what do they stand for?
Reinforcement learning from human feedback.
Okay,
yeah.
I knew that.
So
Oh yeah.
Is this like the complete post-training phase or something?
This is one of them.
Okay.
Yeah, this is how you get it to reason. So you have your big data, set, you train your model off of it.
Yeah.
Cool. Now we want to get this thing to reason. I won't be going over the original RLHF. I'll be going over GRPO because RLHF is kind of the broad idea. Usually use something called PPO, and PPO was originally developed for normal reinforcement learning tasks.
Like robotics?
Yeah, or like cart pull. So it is pretty much the best algorithm for reinforcement learning. Like there are other algorithms, but if you just use PPO, it's basically as good. And I think, was it OpenAI who made it? I think it may have been who made PPO. Whenever they were actually open. And this algorithm, yeah, there exists a time when OpenAI was open, and that's kind of the go-to method. I'm going to talk about that real quick, but GRPO is the new method, and I really think that this method is a lot better. So, yeah, we'll go ahead.
I have another question on the align model. So
yeah.
Are we adjusting the align model, like the weight of the align model?
You'll see how we do this, but basically you take your supervised model and you want to change the weights so that you get it to the aligned model.
Okay.
Yeah.
So aligned model is the RL part that we want to like achieve, and then the reward model.
Yeah, I mean we'll see how it works.
I need to know now, Gabe.
I'm sorry.
Now. So
all right, here you go. So the main idea is, I guess we should probably wait for him to get back. We'll wait because I'm gonna
nice weather today, guys.
Yeah. What a fantastic day to be outside. Unfortunately, we're inside.
Unfortunately, no. We are.
You guys could probably give a lecture on Dallas Power in front of Dallas on a big screen.
We'll scare everybody away. Welcome to SMU GRPO. Let's pop up some formulas.
Imagine doing that during a tour group. They'll be like, I can't do this in college.
Everyone, they'll be like, I'm sorry.
They'll be like, this is the level.
Instantly walk away from the group. Nope, I'm sorry. I can't do this.
We'll be talking about this stuff on the lawn for a picnic, and they're talking about GRPOs.
Yeah, so we all know PPO, right? Everybody agrees. Oh yeah, cool. This is a formula.
Will you be explaining like the motivation of why?
Yeah, I'll be talking about that. Basically, like PPO was originally developed for reinforcement learning tasks, which is like, how do I get an agent to move? And PPO has, like, for reinforcement learning, you have two things. You have exploration and exploitation.
Okay.
So let's say I have a model. I want to know, like, I have some model, and I can either, so usually for reinforcement learning, you have a reward, and your model is trying to maximize that reward.
Okay.
So there are two ways there are two problems, or two problems, I guess you could say. One is, how do I know how much I need to exploit the current kind of, like, the current state of the world I know? So let's say I know, what's a good task? Like, let's say I'm trying to drive a car as fast as possible to a destination. So my reward is like the inverse of how long it takes. So I get really high reward if it takes a shorter amount of time. So let's say I find a path that's pretty good.
Okay.
So exploitation would be, I'm going to just take that path because I know it's good. But let's say there exists another path. If there exists another path, I don't know that path exists unless I do exploration. But to find that path, I may need to find suboptimal paths before I get there. So you have this trade-off. You have this exploration versus exploitation trade-off.
So it's always maximizing the reward function?
It's not always maximizing it, because if it was, that would just be exploitation.
Okay.
So you need this trade-off, and PPO is pretty good at that. Now, with this, you have a model that knows. So people are like, oh, reinforcement learning is coming back because of this. I disagree, because this model already knows how to explore its space. So all you need to do is, like, exploit. So that's easy to do. So no, reinforcement learning is not coming back. It still has a lot of problems with it. At least that's my current claim. All right, cool. We can go over the formulas now. So yeah, the main idea is you want to maximize this reward, and we're going to formulate this as a loss function. So we're maximizing this. Yeah, I'll just break this down. It's not too bad. I'll actually break it down. Actually, I could break it down first. Yeah, I'll do that. Yeah, so I'll break down GRPO, and then I'll explain PPO versus GRPO. So the main idea is we want to maximize some reward, and the way we're going to do that is we're going to have some function that tells us our reward. And like I said, PPO is good at exploration versus exploitation, but all we need to do is maximize the reward. So for example, say I'm given some policy. In the language of reinforcement learning, we're calling our agent a policy, or our policy. Our policy is how our agent acts, but whatever. That's going to be our LLM. So we train this LLM, this big LLM. We're going to call this a policy pi with parameters theta. So that's just our policy model we're trying to train. In the language of reinforcement learning, you have this action space. Your action space is like, I want to move left, I want to move right, I want to move up or down. So usually you have a probability distribution that says, oh, I want to move right, and there's like a 50% chance that under the current data I have, it's 50% chance I move right, stuff like normal probability stuff.
Is the no probability even distributed?
No, because if it was, then it would be random.
Yeah.
It would be
So-
that'd be useless.
So we're adjusting that probability.
Yeah.
distribution.
Well, your model outputs a probability distribution, and under the language of reinforcement learning, I'm relating the two languages because you'll hear both. It is called an action space, and the action space are your actions you can take in your environment. And for an LLM, your environment is these sentences that you're generating. So it's a very simple environment, and your action space is your probability distribution over all your words. So every action is a single word. So imagine I have a distribution over the possible movements left, right, up, and down. That's the same thing as if I had a probability distribution over 4 words.
Yeah. Okay.
Yeah, it's the same idea, except we have like 32,000 words instead of 4.
Right.
Well, sure, tokens, whatever. Words, tokens. Yeah. So it'll be like it's your distribution, your output distribution.
Right.
So that's our action space. So our policy pi is outputting that. We already have this. So policy pi with parameters theta, that's going to be our policy. Policy pi with parameters theta old is going to be a reference policy. You'll see that in the formula. But this is just some old policy that's static that we're not training. This is so we're going to be able to get these relative probabilities. And then we have this formula here, or this thing here, which is saying our policy given a question. Oh, I should probably talk about the data set. The data set is going to be question answer pairs. So Q is a question, A is an answer. That goes with that. So in terms of GRPO, you can think of this as if I were to give you a question, what is like 1 plus 1? The answer could be um, the value of 1 plus 1 is 2 or something like that. For GRPO, we're going to need an exact value to get this working, but we'll get to that later. But just question and answer pairs.
Like exact token?
Like not one token, but like you're going to need an easy answer, or you can use a reward function for that. We'll talk about that later.
Yes,
Yeah.
so the question and answer phase, when you're saying that the answers, are these like from humans or like are they like generated by the as an example?
No, so that's a good point. So question answer pairs. Let's say they're from, since we're doing RLHF, this would be from a human. So like you have a human go and make a bunch of these. So like let's say I have a human, like I give it some. You can get it from an LLM or you can get it from a human. So the two ways you can get it is I have this LLM, or I have this data set of a bunch of questions. I have humans answer it, and they go through the entire question and they write out this proof to answer it. Maybe it's a math thing and they write out the whole proof, or maybe it's just a conversation that can also be your answer. So, or you can have a LLM do it. Like you basically have a human talk to an LLM, and this is where you kind of have this ranking. So you can either have a reward that says this is right or wrong, or you can have this ranking model, which basically says this is a good response or a bad response. So like a reward model makes a lot of sense if you're like, oh, this is math. You got the value 2. Good job. 1 plus 1 is 2. While your ranking model would be different. Like let's say I want a model to learn how to be nice. You can't say like, good job model, 1 reward for being nice. Like that, you can't like program that. So this is where you need humans to kind of go in. And this is where you get the, like, you know how GPT will say, here are 2 responses. Tell me which one's better. That they're using that to train a model. And that model basically says, here are 2 responses. I need a human to tell me which one is better. And given those responses, given those better responses, I can train a model that says this is a good response versus this is a bad response. And that'll be our reward model. So you can either have one that is based off this is the right answer, or one that is based off humans say this is a better answer. And they're equivalent because they're equivalent. Just one, you have an easy reward, and the other, you need to train a reward model.
But how would they train their model with that good versus bad answer?
You generate a bunch of data, and that's why ChatGPT collects a ton of data. But once you have all that data, what you usually do is you take your LLM that you currently have, and you replace the head with a head that says, is this a good or is this a bad answer?
So just classification head.
Yeah, you just change out the head, the classification head over your entire vocabulary with a classification head that's binary.
Okay.
And since it already knows a ton about text, and it does pretty good with that. So now you have a reward model, and your reward model is this thing, reward or ranking model, but that's one of those 2. And that's this bottom part here. So you have this reward.
Thanks.
Yeah, that was a good question. I should have probably talked about that, but now you all know. So this here is going to be our output. So this is our policy. Given a question, it's going to output a sequence. So this is O less than or equal to T is the set of tokens that the policy responds with. So we're essentially sampling from our policy. This is what it gives us, and that's just the response. This is the answer. You could think of it as the answer that is sampled from our policy. So O less than or equal to T, that is the output of all tokens up to token T, which is the current token that we're looking at. So if you have a question, that could be what is 1 plus 1? So that could be up to, I don't know how many words that is, 5 or 6. So T is equal to 6. You give this to your model, it outputs, the answer is 2. And then T would be the last one, and O would be the answer is 2. So given a question, sample response. This here, so this is brackets OI to the power G, and then I subscript I is equal to 1. This is just sampling G, a group of responses. So we're going to be sampling a group of responses from our data, and you'll see where that comes, or why we do that in a second. Here, this is pi of, this is a single token that you get. So instead of this here, which is pi less than or equal to T, this is sampling a single token. So this is the probability of OT. So let's say this is the question is what is 1 plus 1? This could be 1 plus 1 is, and then OT. So O less than T would be 1 plus 1 is, and then OT would be the probability over all your words.
Yeah.
And specifically, or pi of that would be the probability of all your words, and OT would be the probability of the T of OT. So if that is 1 or 2, that would be the probability of that token. So probability of token OT given the question up to token T. And this here, this is notation for the if output, for the if token in your group G. So you have G, a group of G outputs, and you have I is just indexing G. And Ri is the response for that. So let's say I have a group of 3 responses. One says 1 plus 1 is 2, 1 plus 1 is 3, and 1 plus 1 is 1. Maybe I give it like a reward of 1 for the 2, for 1 plus 1 is 2, and then 0 for the rest. So that's just a reward here. Now, in a normal reinforcement learning context, you usually you could get rewards up to your current time step. So let's say I have like a car driving. I can be like, good job, car, you went forward or something like that. So plus some reward. So sure, there can be this like trajectory of rewards. Here you get a reward at the very end of your what they call an episode. I think that's the language. There's a ton of reinforcement learning language. So at the end of your response, you get a reward, but sometimes in reinforcement learning, you'll have reward up to that point. So you'll get reward for every step. And this is kind of why you see in PPO, why PPO looks the way it does rather than GRPO. So yeah, let's just formulate GRPO one step at a time, and then I'll compare it with PPO. I initially was going to compare PPO in the first place, but since we don't know PPO, I'll do that after. GRPO makes sense. It makes a lot of sense. So what we're going to do is we're going to first start off with this R. So this is a little r. Big R will show up later. Like big R is our reward. Little r is a ratio. So this up here is going to be, this here is just a relative probability output. So what we want to do is we want to train our model to give us better responses. That's what we want to do. What we're going to do is we're going to define pi theta old as this reference policy. So this reference policy is going to be this policy that we have in the past at some time step. Maybe we clone it now and then we train this new policy that will actually give us our better responses. And the reason you have this old policy is because we want to define these relative responses. So what this is intuitively saying is we have this old policy. We know this old policy does so well. We know it's pretty good. It's the best thing we currently have. Now what we're going to do is we're going to train pi theta to give us better responses. And what we're going to do is we're going to define this relative output as this. So you can imagine we have this probability distribution, and you divide by another probability distribution. So what that says is how much more likely is every token or every part of our probability distribution under the new distribution versus the old distribution. So intuitively, if you have a higher probability, this would be higher than 1. And if you have a lower probability, it would be lower than 1. So imagine I have the question, what is 1 plus 1? O of I less than t is 1 plus 1 is, and OIT here, maybe it's 2. And let's say our new policy says it is more likely, then the value could be, say, 2 for that token. Like it could be, it's a higher value, rather than if your policy says it's less likely, then it would be a lower value, like 0.1 or something. So that's what this is saying. This is a reference policy, or this is our reference, this is our ratio, and this is so we get a relative output. And yeah.
Sorry, I'm a little bit confused because what is a distribution divided by distribution?
So that's where your relative policy comes in. So imagine I have a distribution over like 4 words.
Yeah.
If one word is more likely, then the value will be higher. And we're defining this relative value, you'll see in a second. Like we could just take this value and we're like, well, it's this likely. But if you say something is more likely compared to what it originally was, you can define things around that.
So for each word?
Yeah.
Oh, okay.
Yeah, so just think of it as, is this word more likely or less likely given the past tokens?
Last one, okay. The old policy.
Yeah. Is it more likely or less likely than what the old policy says? So that's all this is saying here. And this is for this is for all the tokens, or specifically token OIT, for given past tokens here. So what we're also going to do is define this advantage function. So remember, R sub I is our rewards. So our advantage function is this here, and we're basically going to this here we're going to define as a it's this relative advantage function. So imagine I sample a group of outputs. So if I have 1 plus 1 is equal to, and then it says 1 plus 1 is equal to this value. If I have a bunch of rewards, I can say, well, the value of a reward of 1 is obviously a lot better than a reward of 0. So you define this kind of relative advantage function. In terms of PPO, it's very different. It defines an advantage function in terms of one trajectory that you form, which doesn't really make any sense. Basically, it says like you have this decay in terms of this sequence output, but that doesn't make any sense because if I generate a bunch of words, like it doesn't make sense to decay the value at the end at all. So basically in PPO, you have this trajectory that you generate. So like I'm navigating a car and let's say I hit a wall. So that's a reward of like -1. What you say is you like decay all the actions that went up to that. And you're like, well, I took a right at the very beginning. That doesn't really say much about me hitting the wall at the very end, but I went forward at the end, and that says a lot about me hitting the wall. So you say, well, I want a very negative reward for that last action, and I don't really care so much about the current action. But here, you're generating a sequence. You're not driving a car into a wall. You're generating a sequence that's either right or wrong. So it doesn't make sense. Like your entire sequence is either right or wrong. It doesn't intuitively. There's no decay factor there. The decay doesn't make much sense. So instead, what we're going to do is we're going to define this advantage function in terms of this group of sampled outputs we have. So imagine we have a group of, say, 16 outputs that our model responds to. Same prompt. What is 1 plus 1? Or something like that. So output 16 responses. What we want to do is we want to say this response is better than the other responses. Because you can either say, well, like let's say I have a value of 1 for my response. That doesn't say much. But if I have a value of 0.5 versus a value of, say, -1, that says a lot. That has a lot more information than a value of just 1. So we're defining these. Yeah.
Sorry to interrupt you. It's regarding, you said the decay part. Right? So in that sense, you're trying to say that the last action that it made in sequence, only that is considered before for doing the new change in the policy.
So that's what you would normally do for PPO. Like the last action you made is like the most important, and then you decay that to the past.
So you're saying that the next probability in the trajectory is always going to depend only on the previous state, not on all the other states.
No. So the decay factor is saying what's your reward for every state. So if I'm like driving a car, I have a bunch of actions. I can turn left, right, and you make all these actions up to some point where I hit a wall. And the decay factor says the reward, the negative reward at the very end of my trajectory is more important than at the beginning. Because at the beginning, it's like, well, I don't know, I could have gone left, and that's probably as good as if I went right at the very beginning. But the last state where I like went forward into the wall, that's like a very big penalty. However, with text tokens, that doesn't make much sense at all. Like if I have a bunch of text outputting the value of 1 plus 1 is equal to, and then it has like a bunch of proof, and then it says it's equal to 2. Like the entire response is either right or like it's pretty much either right or wrong. You don't really have, well, if it generated the word is at the beginning, that is better than the word the. It's like, no, it's pretty much the entire response is right or wrong. So instead of defining this advantage function in terms of just one trajectory, we're defining it in terms of a bunch of trajectories. That's a big difference between PRPO or PPO and GRPO. I'll go to the advantage function in a second after I define it here. But basically, you have this reward here. So this is a bunch of rewards. You take the mean of the reward and you take the standard deviation. And yeah, you basically define, you have a bunch of rewards and you define it, or you normalize it. So intuitively, if I have rewards if I have like if I have a bunch of rewards, you'll have one in the middle at 0, and you'll have some that are very positive, some that are very negative, and that basically allows you to define this relative value, rather than an absolute value that says you have a value of 1, good job. You have a value of -1, bad job. You have these relative values that say if I generated a bunch of responses, it is better for me to generate, say, a token of 1 than it is for me to generate a token of 2. So that's what you get. And this is more helpful if you have, say, other things. For example, I can, instead of just me saying you're right or you're wrong, I can say, like if I have a neural reward function, it can say, well, this is like 0.7 reward, or this is like 4.5 reward, something in the middle, versus a reward of like 0 or 0.1. So you get this relative reward here instead of this absolute reward, and you get it with respect to the group that you sample from your policy. So does that make sense? Yeah.
So we have a ratio, and the ratio minus mean over a standard deviation, that's just a normalization.
That's so you get it with respect to, so that's so you get it with respect to all the other rewards in your group. Because if I just give you a reward of 1, that's not helpful. Like if you give me 2 responses, well, it's defining this relative reward.
Right. Yeah. Sorry. Yeah. Sorry.
Which we're calling an advantage function.
Okay.
Yeah. So under.
But like you're using ratio minus the mean over this.
Oh yeah. No, that's a good point. So in the paper I use, they have little r. This is supposed to. I forgot to change it. No, thank you for pointing that out.
That's big R.
That is big R.
That makes a lot
Yeah.
more sense.
Yeah. That is big R right there. Let me change that right here. In the paper I used, they put little r, and I'm like, that's wrong. Yeah, that should be. Yeah, they did.
So normalizing it on different form.
Yeah, so this should be big R. The rest should also be big R. So you're normalizing. So you take your reward and you normalize that with respect to all the other rewards.
I didn't even think about that.
Yeah. No, I think I'm gonna email the authors and be like,
Yeah, because
What
you
do you
said
want?
reward and like that makes sense, but it just doesn't match.
yeah, let me block that out here. It's gone. Wow, that's so much better. Yeah, thank you for pointing that out. We will. Oh, come back. Yeah, there we go. Okay, and then yeah, good enough. Fill. Where's the outline? Never use Drive. Whatever, good enough. I'll change it later. All right, there we go. That's better. Yeah. So relative reward. How much better is this reward compared to all the others in the group? So that you have this relative reward, so you know how much you're changing it. And the advantage function, what we're going to do with that is we're going to say, so our policy generated something. Our policy took these actions to generate this output. The advantage function is saying, get under this trajectory that you took. This is how good it is. So we're going to multiply the two together. And you get this here. So intuitively, if I took a good trajectory, I will multiply it by a higher value. And if it took a bad trajectory, I'll multiply it by a lower value. And since you want to maximize this, you just maximize it. Pretty intuitive, right? I took this trajectory. This is what the reward I got. This reward is better than this other reward, which was a bad trajectory. So I'm going to maximize this. Therefore, I'm more likely to take the trajectory I took before.
But you're training that over your entire like action space.
Yes. Well, since you're using softmax, if you maximize the likelihood of one token, it minimizes the likelihood of the rest. So you only take that one token, but it forces the other probabilities down if you're increasing the probability. So that's basically what you're doing here. You're saying, I have this actually is bit little r here. This should be little r. This should also not be little r. Let me change that. Come here. There. Put that there. Little r. Whatever. So yeah. Does that make sense to everybody? Pretty. This part's pretty intuitive. So now what we're gonna do is, since we have these relative, expanding this function once more. Since we have these relative values, what we're going to do is we're going to define this trust region. So intuitively, if I have let's say I have a bunch of rewards. Let's say I have a ton of rewards, and let's say I have like this massive outlier. If I normalize it, it'll be really large. Like you'll have this crazy outlier, and what you will end up having is, like, imagine I'm doing gradient descent. Like obviously you don't want a big step size, and if you have a large gradient, it'll take a massive step size and it'll kill your model. It's the same exact idea here, except instead of taking steps with respect to, well, you are doing gradient descent. It's just intuitively think of your model as this point in space. This point is going along your gradient, and imagine it takes a step size and it kills itself. We don't want that. So what we're going to do is we're going to clip it, and we're going to say, all right, so I see you have this, or Actually, it's not with respect to the advantage, it's with respect to the ratio. So imagine we have this old policy, our old policy has some value. Imagine it assigns like a pretty much a 0 probability to a like 0.00001 to say token, like if we say, what is 1 plus 1? Let's say it assigns 0.00001 to the token 2. Let's say our new policy is pretty good, and it assigns a probability of say 0.5. 0.5 over 0.00001 is a massive value. So what you're going to end up with is a massive step, and you take that step and your model kills itself. So what you do is you define this trust region, TRPO, trust region policy optimization. This was actually before PPO. And what you do is you say, well, I'm just going to clip it. And you clip it. And that's what you do. So what we do is we say, all right, so I want the minimum between this ratio here and this ratio here, and you clip it, and there you go.
So, sorry, what does like clipping do mathematically? So like, let's say we have a super large value, let's say like, I don't know, 5 million, but you know, yeah, we don't want that. So, what is it gonna clip that into?
It clips it into this epsilon ball here, so in between 1 minus epsilon, 1 plus epsilon. So if it's larger, it becomes 1 plus epsilon. If it's smaller, it becomes 1 minus epsilon.
Is it scaled, or is it just,
No, you clip it. You clip it
just
off.
clip it.
Yeah.
So like everything greater than 1 plus epsilon is just turned into 1 plus
Yeah,
epsilon.
exactly.
Yeah.
So you're saying it's similar to a sigmoid function?
No, because sigmoid's function is small. This is more of a like.
No, in terms of clipping the range of the values.
No.
As great as.
Because sigmoid or it's like a hard clip. Like
Okay.
as soon as it hits this value, it's clipped. But like sigmoid is more of a soft clip. Like you can go to infinity and you're fine.
Okay, fine.
Yeah,
Yes,
because sigmoid would push
Yeah.
this into the range of 0 and 1, and you cannot have values outside of that. This you can have values outside,
Okay.
and you cut them off all off, and they're all equal.
What would happen if we use sigmoid?
It wouldn't do good. You would it just wouldn't do anything.
But it wouldn't that like still be scaled?
I guess what would happen if you used it? I don't think it's as good. Like I think if you use a sigmoid, like that clamps it between 0 and 1. And I guess you could scale it between 1 minus epsilon and 1 plus epsilon, and I guess you get nicer. I think the gradient becomes bad.
Oh, okay. Like it's just too much to calculate.
I think it just becomes bad because sigmoid has the vanishing gradient problem. You could also use KL divergence to clip it, but that's also expensive to compute. So here we define a KL divergence, and this is basically saying, so remember R is policy theta over policy theta old. This is policy theta with and policy theta ref. So this is our initial model. The other one, policy theta old, is this model that we're going to be updating, just not as much as policy theta. And policy reference is the initial supervised fine-tuning model. And what this is saying, well, we have our policy we have our initial policy, our initial model that we trained. We don't want it to deviate too far from that. This is actually kind of stupid because under this paper called DAPO, it says you don't need this term, and if you have this term here, it actually does worse. So you actually don't need it to be close to your original model, but intuitively, that's why they have it there, and it's still under debate on whether it's good or not. But I put it here because that is how GRPO is defined. Finally, you add some expectations. Let's go. So this is the formula we had in here. This is our advantage. This is our ratio. This right here is a average over your sequence. So you have a sequence of this is the average over the output, a single output. This is the average over the group. So you average over your entire group, you average over all your token outputs. So intuitively, if I have this chain of tokens that led me to a value of 2, that entire chain is going to get the same amount of say in how you update your model with respect to this loss function here. And you're maximizing this. And then you take the expectation over your data set. Oh, you're good. And then you take the expectation over your data set and model, which is basically saying sample from your data set and model.
That's a question. The beta for the KL divergence, is that like a regression parameter?
The beta?
Yeah.
Yeah, it's like you can, well, it's how much do you want to weigh the KL divergence? Okay. So I guess it's like the regularization parameter.
It's a hyperparameter.
Yeah.
Yeah.
Or you could just not have it and do better. Yeah, so let's talk about PPO versus GRPO. So this is GRPO. Hopefully this makes sense. Basically, you're maximizing this. You have your model, You have your model generate you a group of outputs, and you say this output is better than this output, and then you have your model maximize, or you have your model optimize that such that it'll increase its reward, and to increase its reward, it's just going to, well, you have this loss function, and it's going to try to increase the outputs that are, or make the outputs that are more likely for the good, for the high rewards, and make them less likely for the low rewards. And since you have negatives and positives, it works out well. And you have negatives and positives because you have your normalization. What's up?
What's the, sorry, I know you mentioned it earlier, but what's that, the QA?
This is expectation over your data set, and this is your expectation. So this is expectation under your data set. And what that is saying is sample your data set. Sample, add a for loop over your data set. So these two here are closed form, like you have your entire group and you have your entire output, so you take a mean. This here is an expectation over your data set, but since you aren't going to do this for your entire data set, this is do batch gradient, mini batch gradient descent.
You're just, so you do each batch.
Yeah, so it's sample a batch of data. This is sample a batch of data, and this is sample from your policy here. So this is sample an output.
Okay.
And these two here, since you have your entire group and your entire output, you take a mean over your output.
Wait, sorry, how's that sampling your output?
What?
Like
this one?
Yeah.
You just give your model, you just sample it.
Because D is DI, right? So that one data point.
Which
and
one?
Then over the old.
No, this is D comma.
That makes so much sense now. Sorry.
Yeah.
Oh my God.
Yeah, you're good.
I thought that was.
No,
I thought that was I.
You're
That
good.
was so confused.
So I have this demo and code. So I have this code here. I'll go over PPO in a second. Just want to mention I have code here that I wrote. It does pretty good. Basically, you give it a question. Or I have the script here, which basically goes through and trains it. I can go over PPO, and I guess we have time. We can go over that. I have this collab here. If y'all want to try it out, I'm going to send out the slides in a second. I'll send it out after. But basically, it takes this pre-trained model I had. You're going to need to upload your Hugging Face key. It downloads the model, and it samples from it. So you can always play around with that if you want.
Is it?
This is Llama 3.
Oh.
3.1.
8 billion?
Yeah.
Oh.
Yeah, and the QA data set is in
So this is a math data set. So if, like we talked about earlier, like if you have a model, or if you have like math, you can easily say this is right or this is wrong.
Yeah.
And that's really easy to do for me because I can get an output and I can say this is right or wrong. And it's right if it's in the data set and it's wrong if it's not. But if you don't have that, like if I wanted to do stuff with like something that isn't right or wrong, something that is like, is this model nice?
Mm-hmm.
How do you get this model talkative? You need to train a reward model, and then you just swap out your reward function with your reward model. But it works in both cases.
Makes sense.
Yeah, and then there's this Hugging Face GRPO trainer. If you actually want to train something, you should use this. If you want to see how things work, you should look at my code because this code ain't doing that for you.
Yeah.
So if you are curious how this works, I have code here. Basically what you do is you sample a bunch of outputs. Don't take the gradient at all. You don't want the gradient because it'll blow up. Once you have all those outputs, you then just throw it through GRPO. You do a few optimization steps, and you do that over and over again.
So reinforcement learning doesn't rely on gradient at all?
It does. You're doing gradient descent. You're doing gradient ascent. You're trying to maximize your reward. And your gradient is with respect to all your model parameters. Your policy. No, A is just A is just telling you how good this output was.
Oh, just this, like that.
Well, like if I ask you what is 1 + 1 and you say 1 + 1 is 2, then A is saying this is a good output versus all the other responses you gave me in the output. If I ask you 16 times.
Yeah, A is the reward.
Yeah, A is the relative reward. Yeah. It's what's called an advantage. No, it's understand. It's hard with all this notation. It is really annoying to look at.
But it's not gradient. It's gradient in the sense that you're taking the derivative of your loss.
You're taking your derivative of your loss here. This is your loss, J.
Oh.
Because you want to maximize your
yeah,
reward.
that's the entire. Okay, sorry. Yeah. All right.
And all you're optimizing is your model here, right here.
Yeah. Okay.
Yeah. And I have some resources here if you're curious to read more about this. DAPO is like GRPO but better. For example, if we look at this, is there a problem with this? Indeed there is. Imagine I have all the same outputs. This will become infinity because you divide by 0. There is no standard deviation for the same outputs. So
really unlikely.
No, it's actually really likely. Yeah. Well, if it's a hard problem, then it's really likely. So that's actually a problem. DAPO fixes that by just resampling. Yeah, so let me go over this real quick. PPO versus GRPO. So this is our GRPO formula. And there's a few big changes. So you can see that the basis is basically the same. So look inside these parentheses here. This is our GRPO function here. This is our PPO function here. Same exact function. The only difference is in the advantage and your expectations and this KL divergence term, which is actually bad, and you remove it. So we're not going to worry about that. So you, instead of generating a single trajectory and optimizing over that one trajectory, which is good if you're driving a car because it's hard to get data, here it's super easy to get data. You're just like, I want more data. All right, I'm going to go collect some more data. Go model. Go give me some more data. It's super easy. While in a normal reinforcement learning setup, you can't do that. So you have to do with what you can, and you only optimize over your single trajectory. Or if you have multiple trajectories, you have less data, so you're optimizing over this one trajectory and you decay your values.
Does single trajectory mean just like one run?
Yeah, one run.
So basically PPO is like doing the car thing, like you run into a wall at -1 at least.
Yeah, and then you optimize all those states for all those states. Here instead, we're like, well, we can collect a ton of data, so we're going to optimize with respect to this entire batch.
Like the entire
yeah. So like 16 batch of 16 data, because it's easy to collect this data. Mm-hmm. So that's what you're doing here. It's a different expectation.
Yeah, the case divergence. It says that you're trying to not make it deviate from the original model.
Right, the supervised fine tune or the original trained model.
Yeah, so from the original training model, like you want it to deviate a little bit because you want it to learn.
Yeah, exactly, and so it runs into problems.
So I don't
yeah.
understand.
It is intuitively, it can go either way. So if you add it, it's good. It makes sense to have in some cases. You're like, well, my original model is pretty good. I want it to have like the original knowledge in the model. I don't want it to just become this parrot that can only respond and doesn't know what it's talking about. But also you're like, well, the original model couldn't talk, so I wanted to deviate far from that. So both ways kind of make sense, and if you just remove it, it's better. So there's a paper called DAPO which came out like 2 weeks ago that basically says that. When did this come out? I think it came out literally like March 18th. What? It's April, a month ago. Yeah, so that's that. DPO or PPO and GRPO. PPO, what's originally used. GRPO is what DeepSeek proposed, and it's better because it makes sense. It makes sense for this context. And additionally, we have this here. Basically, this is your discounted sum of rewards for PPO versus GRPO, which is relative to the batch. So either you have one output and you want to optimize over that, you basically have this episode that you simulate, and you have this discounted sum of rewards versus GRPO where you don't have that. So just what I mentioned before, just in a formula here. And then there's this here. One big thing that I didn't mention is you have a critic with PPO. And this critic basically has this value function that you define. So if you look here, you have this value function here. And this value function is this trained model that predicts the value of every state you're in. And that is annoying because now I need to train two models at the exact same time. And funnily enough, it's usually better if you remove the critic under reinforcement learning. Reinforcement learning is in an interesting state right now. So I don't know, if you want to do research, you could probably do it for reinforcement learning and find something pretty cool. So yeah, you don't train a value function, which is another reason to use GRPO. You only need to train one model versus two models. Yeah, it trains this value function here. So if we have this here, critic function, I'm not going to get into that part, but basically you need to train two models for PPO versus GRPO, where you train one.
Wait, what is gay?
What is gay?
Yeah.
You?
No, GAE.
Oh, yeah.
Yeah.
I'm not going to get into PPO. That'll take a while, but basically, I mean, it's just PPO is similar to GRPO. All you need to know is PPO is similar to GRPO, and the few things I've mentioned before. Plus, if you also don't need to optimize this value function. So you're only optimizing your single show up VS Code. You're only optimizing this single thing here. Get out of here.
Is your AI girlfriend finished training?
No, probably died. Yeah, so that's it. No, it's my session is up for the compute node I have.
I'm sorry?
The session I have for the compute node is
like
out.
Super Bowl?
Yeah, the 2 hours.
Yeah.
But don't worry about it. As long as you understand GRPO and kind of the idea behind that, that's good. If not, let me know and I can try to explain it further.
Yeah, this actually makes a lot of sense.
Yeah.
Like for your text and question answering.
Yeah, and that's how you get it to be talkative. Yeah, so I don't know. Go ahead and take a look at this. Here's some good resources. So PPO, if you're curious about that, GRPO, and another GRPO thing, and then DAPO.
So the GRPO doesn't have a value function like a critic at all.
No critic at all, which is another reason why it's awesome.
So like, was it a motivation for them that in the trajectory sense that you're taking only the final like decay part, that they needed to keep a value function to properly use it?
Yeah, I think because if you did decay it, you would need to have a value function to use that decay. So I think there were a lot of motivations against using PPO. Like, one, I need to train a value function. If I don't train a value function, how can I optimize my reward, or how can I optimize my reward? Because I can no longer take this discounted sum of rewards.
Yeah.
Well, I can optimize over this group. So, but it also makes a lot more sense. Like, even if I didn't even talk about the value function, it makes a lot of sense to just optimize over a group versus this discounted sum of rewards, which doesn't make sense because your entire output, it shouldn't be discounted at all. Yeah, so I think there's a lot of reasons to go away from PPO for this. Yeah. Guess if you're curious about the code, I can. Yeah, I don't know. It's pretty simple, but basically, like, oh, you have this script here. One thing with GRPO is you need it to output you. One thing you need with GRPO that, like, it's awesome, but you need that model to output a correct response at some point. If it doesn't, you get infinite. You get the same value because like if it doesn't output the correct response at all, you get the same value, and you're trying to optimize this advantage, and this advantage is always going to be infinite because you have zero standard deviation. So that's one thing. And with PPO, you wouldn't need that if you had a good value function. Not necessarily. So yeah, I mean, GRPO isn't the end all be all, but it's pretty damn good.
So on the problem of hard question, what if your answer is like super long?
Yeah, so that's
that would be a hard question.
No, so that would be fine. Like, if your answer is super, well, usually you don't optimize the answer. You're not telling it. You're not optimizing every token.
Okay.
You're saying, model, generate me a bunch of tokens.
Yeah. Okay.
Was your last token, or was your last few tokens right? If it was, good job. I want you to increase the probabilities of all those tokens.
Oh, okay. So let's say like it will generate up, like, let's say it's math.
Yeah.
You ask a question, and then you like go through every single step, and at the end it will give you the answer.
Yeah.
And you just say if that's the right answer, you give it a yes on the whole.
Yeah.
Oh.
Basically.
Yeah. Okay.
That's basically what you're doing, of course, with these relative rewards.
Yeah,
so you're not doing what you normally do with supervised fine tuning, where you're saying, I want you to output this token at this time step. You're saying, generate me a bunch of output tokens. Good job. And you may notice that that only works if it can generate you an output that is right.
Yeah.
So this is why you need to supervise fine tune in the first place. And why you also, or this is why you need to train it in the first place, so that it can actually output that, and it can output something right at all. And and with GRPO, you need to actually output something that's right some probability at a time. But this is why you get interesting things like it like with UC or what you see with DeepSeek, where it generates this big response because you don't force it to generate anything. It just generates this big response. All you're forcing it to do is get the right output. It can do whatever it wants. That's why you see it thinking, because you don't train it to do anything. But I guess to probabilistically, it's more likely to output, say, a 2 if it thought about things than if it didn't. In the example I have here, it doesn't work if you don't do GRPO. So I have this question, this thing here. Don't read it. The answer is 27. If you don't do GRPO, it'll just output you 20. It'll output you like 17, and then it'll output you 11, and then it'll output you like 13. If you do GRPO, it'll do this. It'll say to solve the problem, let's just break this down step by step, and then it outputs you 27. So it is more likely to output the right response. It's basically like training it to do more chain of thought in a way.
Would you think this is what O1 did under the hood, or O1 just
Probably.
Okay.
Yeah.
Well, we don't know, right? Because it's not open.
I mean, you see what happens with DeepSeek, or you see DeepSeek. Like DeepSeek was trained with this.
Yeah,
they came up with this.
Obviously. Yeah.
And you see the outputs of O1 are similar. So why would it not be trained under the same regime?
What about have you read about S1K?
No.
It's a Stanford paper that they did, like used 1,000 training points.
Oh yeah, I saw that. Never mind. Yeah, good for them. I mean, it's not going to be good.
Read it probably. I just can't get into it. Anyway.
So, I might be wrong here, but that like the analogy of having reinforcement learning, like an intuitive way, would be that it's trying to get an out of distribution generalization.
I would say it's the reason I would say it's in distribution, because if it was out of distribution, it would need to do exploration, and here it doesn't need to explore at all. It just needs to exploit. It pretty much just it doesn't really need to explore. It just needs to exploit and increase the probabilities of these trajectories that it knows are pretty good, but it doesn't. It won't necessarily do all the time. So it's still in distribution. Like it's still like the model may generate this at some point. And that's not unlikely. It's kind of increasing that and convincing it to think about things, generate these sequences of tokens that are more like that make it look like it's thinking, generate these chain of thought sequences. So I would say it's still in distribution, and that's why we don't use that's why we don't have to have it explore at all. Like it doesn't really explore. Like that's why I'm like it kind of is cheating with reinforcement learning. Like we're using reinforcement learning, but not for the entire reinforcement learning task.
Yeah, like it defeats the motive of even doing
Yeah, like it makes. My claim is there's an underlying thing optimizing this that we don't know that isn't really reinforcement learning. Like there's some underlying theory that's actually optimizing this that is kind of hidden behind the reinforcement learning that we're throwing at it, because it's not really doing reinforcement. Like it's kind of doing reinforcement learning, but also kind of like but not in the original reinforcement learning sense. Like it's kind of moving away from that. So it's kind of reinforcement learning, kind of not.
I guess you're trying to train for a certain response, but not forcing it to answer a certain way, right? Because it's not like you're fine tuning it.
Yeah. Well, you are fine tuning it. It's just you're fine tuning it so that it outputs a response.
Right.
It gets the right answer.
But you're not you're fine tuning it for the sake of like this one last output. You're not fine tuning it with, oh, you need to like the chain of words of mask causal LM of your next word prediction.
Yeah.
Right. So.
Like my claim is that it is like we're using reinforcement learning, but there's an underlying optimization that's happening hidden behind reinforcement learning that we're actually doing.
Does it just look like a fancy fine-tuning mechanism?
It basically is, except normal fine-tuning is fine-tuning token by token. Here you're increasing the likelihood of tokens that are good.
Token like after, right? That kind of sounds like. Doesn't that actually sound like PPO?
Well, PPO does work.
Oh no,
it's
I
it's
know.
just not as good.
Yeah, but like I'm saying like if when like if you think about it for the sake of reinforced learning, if you're just like adjusting your weight for every next token, isn't that kind of like PPO?
Well, PPO is reinforcement learning.
Well, yeah, I know. But
Yeah.
like,
Because there was the big difference. Like PPO and GRPO both do the same
yeah,
task.
Yeah,
Like
yeah.
they're both optimizing the same thing. It's just this is way more efficient with LLMs. That makes more sense.
What's the fine-tuning data set look like? The math problems, it's also like chain COT structures or just 1+1=2?
It looks like let me
you don't have a CSV in here, bro.
no, I use Hugging Face. I have it somewhere here. Where is it? Where's dataset?
Yeah, I'm still trying to understand the motivation. Why do they want a reflection?
Well, it's you can optimize. Well, you use this for two things. Like you can use it for making it nicer, which is what it was originally made for, and making it reason more. And the reason you would want it to reason is because you basically make it do more chain of thought. And if it does more chain of thought, it is more likely to output the right response because the probability distribution kind of narrows in a way. So yeah, this is what I trained it off of. It has it's simple tasks. It's not very hard. But like DeepSeek did harder ones. So like I would take this question, I would give it this question. It's not a hard question for us to answer. It's,
Zooming a little bit?
sorry. Is that better? There we go. So yeah, and I don't care about the answer at all. All I do is take this. I just take 42, and I optimize it to do that. I remove the rest of this.
So when you train fine-tuning the model, you don't take the thinking process.
Right. I don't take that at all. I only say you got 42. That's a reward of 1. You did not get 42. That's a reward of -1. And then you take like 16 of these outputs. So you say, all right, model, I'm going to give you this prompt, output me like 16 of those. So my group is 16. And the ones that are 42 will be given a reward of 1. The ones that are -1 will be given a reward negative, or the ones that are wrong, reward -1. And then you take this advantage function saying, like, depending on how many ones and -1s I have, it'll tell you how much better is this output compared to the rest. And you can make it better, like, maybe you add something in there saying, well, at least the response looks pretty good. I'm going to give you a reward of 0.5 or something like that. I actually add something else, which is what DAPO added, which is like, oh, this is way too long of a response. I don't want that. I'm going to deduct some points because it's too long. So you get this relative reward makes more sense whenever you don't just have ones and -1s. But yeah, it's basically just remove the answer. And the reason they have answers here is because they initially did supervised fine tune it on these answers that were manually created, and that didn't work that well because now it didn't really learn the reason. Just supervised fine tuning. Yeah. And this is the original. This is an OpenAI data set, and that was what they initially did to get it reasoning. But it is much better if you have it do this itself.
So somehow it's more effective to just use the GRPO over the, let's say, 42
Yeah.
and supervised fine tune the whole thing.
Well, one, it finds the answer itself.
Yeah, like
it's hard to not add a
exploration.
human words to it because there are no like words to explain it, but it increases the probability. It finds its own way to increase the probability for this.
Right.
Versus the
Like
other way.
It's kind of an exploration, right?
It's
like
it kind of explores, kind of it's still in distribution, so it's hard for me to say that.
okay, sure.
I have a point to that. So like,
Yeah.
So the question answer data set when it's created initially, does it have to be created in such a way that it's following a chain of thought reasoning mechanism?
Yeah. No, so you don't need the answer at all. You don't need this at all here. You just need the answers, and you can do this reinforcement learning part. However, it would be better if you had this chain of thought response, because what if the model never gives you a right output? Maybe you can help it a little bit by giving it some chain, like these intermediate steps.
So like maybe like, oh, get 36, get like 84, and then finally 42.
Well,
like that.
well, you can see here that's what the model basically did. The model figured that out here.
Oh yeah, no, I know, but like if it's like a really hard question problem and you can't figure it out and you just said like give it some intermediate
Yeah, maybe I give it this
steps.
part here.
Oh, like in your question.
Yeah.
Oh.
But
oh.
under GRPO, you don't need that, or under reinforcement learning, you don't need any of this here. All you need is 42.
I guess it's yeah, I guess it's good like you said, like it's kind of good because like it's coming up the reasoning itself, right?
Well, that's why you train it with reinforcement learning. Otherwise, you would just
Yeah.
use fine tuning.
Yeah, exactly.
Or you would have a reward model telling you if this is like a nice model or not, or if it's a good or something like that.
Like do a little sentiment analysis. And
Well, that's why GPT asks for 2 responses sometimes,
Right, yeah.
because
Or
it's
human,
training. Yeah, because it's using you to collect data
Right, yeah.
for reinforcement learning.
Exactly.
That's why it's fun to select the wrong one. Bad data for them.
We are the exploration phase.
Yeah, we are. No, it's a good point. Yeah, that's a good way of putting it. We basically are exploring for the or for the model. It doesn't do it. If it did, it wouldn't do very well. That's why reinforcement learning sucks.
This is going to get on your nerves so hard. But what if we do this, but for GNN?
Why would you throw a GNN in it?
Well,
GNN is in the graph neural network.
yeah, like you were saying like GNN is just bad, and then we need something for it.
Well, it needs to generate a trajectory of outputs.
And also you're saying to create a question as a node and answer as a node and connect them? Is that the way you're
Nah, bad idea.
Let's say use PPO for GNN.
Bad idea.
So you already know.
So like PPO works for reinforcement learning tasks, but it also works for this task because you have this initial response, which is already pretty good.
Right. So you argue this is good only because like your original model is
Yes,
good.
that is my exact argument actually. Yeah, this is only good because your initial model already knows how to explore its space really damn well. If you have a model that doesn't know how to explore its space, it doesn't do too well, and that's why reinforcement learning isn't that good.
Thank you very much.
Thank
I will end it there. Yeah, thanks for coming.